pick up here. I will attempt to keep an eye on questions as they come up, but for the moment, um, when we're looking at understanding these coordinates and what the algorithm is asking us to do, it's about tracing the steps of a direction vector from tail to tip and understanding how to move those. So it's this is a process that you need to memorize. You don't need to memorize the uh, formulas and things that we're using for a lot of this, but you do need to memorize the actual process for how do we evaluate these things. And so we will work on some additional worked examples here shortly. Some of the things that you want to pay attention to are making sure that you're always dividing these values so that all values are less than 1 as you go through these steps, because if you forget to do that, creates all sorts of issues. Multiply terms either by A or C to rescale them relative to the axes along which they align. And then you construct the vector by placing the tail at the origin and stepping off in each of the axes, first in A1, then in A2, then in A3. So it's something that again, a little bit of practice kind of helps. This is just a kind of coordinate system that you guys haven't used before. So it's 4-dimensional instead of 3-dimensional, and that can create some confusion. So when we're dealing with HCP, what we're going to do is we're going to start by taking these, removing the brackets. We have to add in our negative signs so that we don't forget those. I would say that's probably one of the biggest areas where students will make mistakes and end up dropping points, is they forget the bars, or they forget that the bars mean negative, and they end up with some incorrect results. So -1, -2, 1, and 3, we divide by the largest value, which is 3. We get nice fractions in thirds, which happens to be convenient for this scale in this example. And you do -a over 3, -2a over 3, and a over 3, and then all the way in C, all 3 steps, since these are divided up into thirds. So starting at O, you go back 1 in A1, you go back 2 in A2, and then go forward 1 in A3, and then you go up to all the way 3/3 in C to the top. And then you draw your vector, and that's what's shown in green. So this is a helpful way to remember how to walk through the process for these. So when we're going the other direction and we're trying to figure out what they are, we're trying to understand the crystallographic directions. You take the tail coordinates x1, y1, z1, and the head coordinates x2, y2, z2 in terms of the 3 axes. So it'll be a1, a2, and z. You subtract the tail from the head, and then you kind of work your way backwards. Each of these steps is fairly important. We use a transform here for calculating our u, v, t, and w based on the u prime, v prime, w prime that we get from our square brackets, and we end up with u, v, t, and w in our enclosed brackets. So this is one of the ones where a lot of confusion happens, and that's why I wanted to sort of touch on it a second time. So if the tail is at 0, 0, 0, and the head location is at 1, 1, 0, the reduction is the same since none of these are larger than 1. So in brackets, we start with 1, 1, 0, then we plug in for our formulas. We calculate U based on the formula. We calculate V, we calculate T, and we calculate W. Each of those then needs to be normalized. So we multiply through by the common denominator, and we end up with 1, 1, minus 2, 0 as the indication. So even though this is plotted in 3 of the axes, there's still a 4th axis coordinate, meaning 0 or no interaction for this crystallographic direction based on 0. And I'll see if I can pull in a couple additional helps for you guys to visualize a little bit more clearly what these planes are making reference to, because the diagrams in the book are helpful, but they're not telling you like the full and complete story, which that is not helpful. So there are equivalent planes, and we had touched on this just toward the end last week, where everybody was sort of turning into mushy oatmeal at the end there. 001 is a reference plane. There are other equivalent planes. Basically anywhere along the z-axis. 110 plane is pictured here in blue, and so there's other equivalent planes going along the y-axis. And the 111 planes, those sort of sharp shards that I was referring to as how those materials behave, those again typically along the y or the z-axis, there are equivalencies. So when we're trying to understand these, there are going to be questions that'll ask you about the Miller indices. And what these are is the reciprocals of the 3 intercepts for the plane. But what we have to do is we have to clear them of fractions for fractions and common multiples, because the idea is they're supposed to be a least common reference point. They're supposed to be a reduced number set in order to make reference easier. So if you had a 10, 10, 10, 0, you want to reduce those, because that's going to be a related plane, that is a equivalent plane to a 1110 if we're talking in like the hexagonal space, for instance. So the process for these are start by reading off the intercepts in terms of A, B, and C. Then we get the actual reciprocals for those, and then we reduce to the smallest integer values and enclose them in parentheses. So the intercepts being 1 at A, 1 at A, 1 at B. Get our marker here. Want that to go away. All right. So 1 at A, 1 at B. The infinite value here for C, because it's anywhere along the z-axis. You take the reciprocals of these, so 1 over 1, 1 over 1, 1 over infinity. Reducing those, there's no common integers or least multiples, etc., that need to be reduced there. So the Miller indices are the 110 for this crystallographic plane. And that's what we see referenced here. So the Miller indices of a plane 110, this is how they are determined. So 1, 1, and then infinity, the reciprocals give us, when reduced, our 110. This is our Miller indices for the plane. So another example where it's in a different, along a different axis, 1/2, infinity, infinity, reciprocals, 1/1/2, 1/infinity, give us 200. We reduce this to 110. So there's a typo here. We reduce this to 100. And this is the Miller indices for this particular plane. If we have a triangle or something like that, we need to estimate where these land. And this is much more like the kind of problem like you might see on the test. So this is the thing that you want to understand what it is that you're doing. You start with the intercepts at 1/2, 1 3/4, because this is about halfway. This is all the way at 1. This is about 3/4 of the way up. So it's definitely above the halfway mark, not all the way up. So it's about 3/4. This will be, in many instances, a little bit of a judgment call as far as where all of this happens. Okay. You take the reciprocals of those, you get 2, 1, and 4/3. So then to clear the fractions, we get to 6, 3, and 4. There is no least common multiple factor going on there. So the Miller indices are 6, 3, and 4. So just as in these other examples, you're going to have other equivalent planes that are continued along the axis. However, they're not going to have the same, they're all going to have the same Miller indices. So whether this was scaled up or scaled down, the key is, and the reason mathematically for the reduction is, even if this were taken at a parallel plane that was 10 times farther out, we would have a 60, 30, 40 coordinate set that we would end up with. And that would still reduce down to the same Miller indices of 6, 3, and 4. So there's also these family of planes that can be shown that are one in any specific region. So the 100 family includes quite a few reference points. It's helpful sometimes to visualize them, but the crystallographic planes are important for a lot of regions. In hexagonal unit cells, the concept is the same. So our intercepts here are 1, 1. In A2, this is infinite because it's going to go along A2. -1 in A3, so it goes backward 1 in A3, and 1 because it goes all the way up to the top. So for each of these, we have a value. We take a reciprocal. Again, these are easy to sort of visualize on the board. This is why we'll work on some additional examples here later this week. But looking at these reciprocals, we have 1, 0, -1, and 1. So the reduction is the same for those, and the Miller-Bravais indices are about 1, 0, minus 1, 1. So this one's not nearly as confusing or unusual. So this is a little bit more straightforward. We want to get a better handle on the atomic packing of the crystallographic planes and think about something like the iron foil that can be used as a catalyst. So it's the atomic packing of the exposed planes is important. So these are going to be interesting the way that they work. In order to understand what that looks like, a 1 0 0. We looked at several examples of these. The difference between a 1 1 1 and a 1 0 0 means that for the 1 0 0, the writing methods on this we'll always have a couple errors here, but we'll work with it. A 1 0 0 is going to be, so this would be the, if this were Y and this were X, this were Z, what we've got at a 1 0 0 is a point here, and that point is going to make that intercept is going to make a basically like a line here. It's going to turn into a plane here that's going to be infinite in the other two axes for 1 0 0. For 1 1 1, it's going to be a little bit different. For 1 1 1, you have your coordinate system. You have a 1 1 1. So we've seen examples of that. Wyatt decides to draw these high-speed marks. I couldn't tell you things that don't make sense. But this region right here is the plane that's formed by that 1 1 1 crystallographic plane. The planar density, we have to go back and remind ourselves what that is. So this is all direction. So linear density is the number of atoms per unit length of a direction vector. So iron, if we're calculating that, this is a good example. The linear density, let's find iron because I think we used that in one of the examples. For most of the time, iron is going to land in body-centered cubic, and I think they gave us, yeah, so they gave us a couple of the pieces for iron. So we're looking at body-centered cubic. So we note that piece of the puzzle. If I'm asking you to do that, there's a couple other factors that we're going to use in the calculations. So this is when not to do build slides, as if you're trying to make a point like that. So B, C, C for our planar arrangement. And then We do like Pig in Toy Story. No time to go back. Got around the horn. That predates you guys by easily 100 years. All right. Um, we have iron, I think, in one of these early ones. Might have been when we were calculating BCC. So this is the unit cell that we're working from for iron. They had, coordination numbers, but we were given I thought we had it in one of these. No, we did chrome here. This gives us the material density, which is not what we're aiming for. We've got this is more properties for iron, but I thought we had its actual atomic radius in one of the ones that we went over. No, because that's all crystallography. There we go. Aluminum. Let's see. So aluminum, but that one is face-centered. Okay. So we don't have that value for iron here in the group. I thought we had covered it in the materials, so I was going to point out where it was on the slide, but that one is not included. So what I'll do is have to pull that real quick from the text. And that way we can show you what those calculations actually look like. So planar density for this one. Okay, yeah, they show there is just on the next group, they show BCC. Okay. I was going to say, I thought it was in the slide set, but I've slept since then. So at below 912 Celsius, iron is in the BCC structure. For the example 100, they give along that direction. 100 is along a 2D representation. The A value is 4 times √3/3 times the atomic radius being 0.1241. So the planar density is number of repeat atoms, so 1 in this plane. So again, a plane being a 2-dimensional slice of this thing, but it's a 2D unit that we're doing the evaluation on. So 4/4 makes a whole. So 1 repeat atom divided by area of the repeat unit, which is A squared, A being this 4√3/3 times the radius. So we get 12.1 atoms per square nanometer. So what that does is that allows us to say it's 1.2 times 10 to the 19th atoms per square meter. This is helpful in terms of how this operates, to get a sense of what the calculation looks like. But we also want to know for the 111 crystallographic plane. So when we have this BCC structure, let's go back to, let's see if we can mark it up here. So we're still in the BCC structure, but now where we were doing just this plane as a 110, now instead what we're going to do is we're now going to do a plane that goes up and down and back. So here we have quite a bit different number per repeat unit. So we have, for each of these, we have one that's in the center that we cross through, right? It'll be easiest to visualize this back on the BCC. That's FCC. Back in the BCC. Yeah, here we go. So what we're trying to do is we're trying to take a cross section that has up to this corner, do that slightly better. We do up to that corner, down to this corner, and across. So we have a fraction, we have a fraction, we have a fraction, and then we have a whole atom that this encompasses in the 111 plane instead. This is probably actually easier to visualize in a SolidWorks example to help you guys to know what's going on there. So I think that's actually what I'm going to do, because we can do a rotated section view of what that plane looks like. So let me pull that up and we'll get an idea based on the dimensions of the iron. That'll make life a little bit easier to see. Because we can do a rotated plane. And some of this stuff just sounds like gibberish until you actually put it into practice. So what I'm going to do is, for this one, sure, we'll do front plane. I'm going to do a little bit scaled up, but use the same ratio for our smart dimensions, because that'll give us a little better reference point. Because we'll see an example of what that looks like, but it's going to be a whole lot more clear in SolidWorks than in their example. So 0.1241 nanometers. We're going to use that in our smart dimensions. So 0.1241. So I'm going to do 100x scale up. Yeah, let's do 100x scale up, and it has to be times 2 because this is the diameter. So this is 1,000. Yeah, it's 1,000 x scale up. So what we're going to do is copy that same dimension and create that. We're going to create that adjacent to each other in SolidWorks so that you guys can actually see what's going on. I think this is going to be significantly more helpful because without it, you're going to be no thinning feature ever. No thinning feature ever, ever, ever. Rule of thumb, no thinning feature ever. We're going to create the sphere just for kicks and giggles. We're going to do not configure the material, but select it. So we're going to do gray cast iron. So we're going to do iron spheres. We need a couple other reference points. In this case, we can go back to our original sketch and we can do a kind of an interesting thing, but we're going to need a couple reference planes. This is why we don't go through an exercise like this all the time in order to understand it. Separation distance needs to be 2.48 over 2 so that our plane for our reference is just going to be intersecting this. This will make sense here in a second. So we need one of those, only we actually need 2 of them. So what I'm going to do is I'm going to do one ahead. I'm also going to do one behind. So I'm going to do another reference, but it's going to be flipped offset, and it's going to be 2.48 flipped offset to get the other atoms where we need them to be. So plane 1, we need that to be considerably bigger. So plane 2 will, as a reference, also change size. So what we're doing now is creating our unit cell here. I'm going to change the view so that we have a square view again, make sure we're dimensionally accurate. We're going to add a sketch to this plane. So we've got center lines. And another center line Because trying to understand what some of these crystallographic planes look like, we can set up a couple reference planes that we can actually see it. It's going to be a whole lot easier if we have a unit cell to reference for this. We're going to do some more center lines here. These are going to be just out here on the side. And we'll set distances. So distance between these two needs to be 2.48. Distance between these two needs to be 2.48. Then we're going to need a couple other center lines. This is going to be just the simplest way to throw one of these together. Unfortunately, unlike Rachel Ray, I don't have a staff that does this for me. And here in the oven, we have an already done version. That doesn't really work in real life. Welcome to engineering. So now we have our intersect points. So we can create our circles, and we can do kind of an array function to make the best of it. 2.48. Here we're going to do bring this down to 1.24. We're going to bring this down to 1.24. See, that is, yes, so that is actually correct, 1.24. I forgot half distance because a squared plus a squared equals square root of 4a squared, and yeah, it'll all make sense in a second. 0.24, there we go, and 0.24, okay. So these will all make sense in a minute. What we're going to do is do an array. Linear sketch pattern on entities to pattern 2.48. And these are our total distance between these is actually going to be a and half of a, which is our 4/3. So we're going to make some adjustments here based on our correct dimensions. 4√3/3 times r is our total spacing, center to center. So this is going to be a little bit simpler to calculate here. This times 4/3 times our 1,000 scaled up value, which is times 1.241 equals 2.8. I'm going to say about 2.8. We're going to go 4 decimal places, make a couple corrections. So I will come back and do a linear pattern here in just a second. So this value divided by 2, 2.8659 divided by 2. So it gives us 1.43295 to account for the intersection just at the right place. This will give us our spacing, so we can now do our linear pattern. We're going to do 2 in X, 2 in Y, and our spacing is going to be times 2 x-axis times 2, and the entities to pattern are this circle, and we're going to flip direction on the y-axis, and we've got all of our patterns there. So we need to cut our circles down the center line so we can do our rotations, and then we can do some cool mirror entities, and that will make life, as long as we've got a mid-plane to mirror across, which will make life a little bit quicker. We'll be able to have this and be able to visualize what this BCC is, actually rotate it in 3D space, and I think make a little more sense of it. So we want to revolve around this axis, no thin feature. We want to revolve this region and this region. And we want to revolve these. Yes, you can revolve multiple species from the same sketch at the same time. Region 1, Region 2, axes of revolution, get rid of the thin feature. There we go. Okay, now we have our intersection. We'll hide these other planes and some of the other gibberish here in just a second, because we want to be able to see these very clearly in what they're doing. So now we want to do our mirror entities. And before we do that, we need one more reference plane, and we need a mid plane. It's going to be easiest to do. Actually, our plane separation needs to be adjusted because these have a larger intersect region than they need to. So I'm going to make some adjustments to the planes first. And edit that feature. That separation distance actually needs to be this far. Okay. So our second plane needs to be this value times 2. Get our dimensions correct, because there is a small void. So we have just immediate contact between those surfaces without actual physical compression. Again, it's an estimated distance, so we're going to be pretty close to accurate. Let's see. Okay, so we have mirror these first. We want to select this object, and we want, rather than a first reference, we can select the front plane, which is also our mirror plane. We could use that as a mirror plane, but we want to do a 0 offset. This will allow us to do a mirror, and the objects will show up in plane, or coincident rather, with plane 2. So it's already got our mirror plane selected correctly. Features to mirror. We want to mirror them about plane 3. So we want to see if it will let us do 2. See if it'll let us do 1. Nope, it does not want us to. There's a couple of reasons why that can be a little bit difficult. So instead, what we can do is we can do it the old-fashioned way on plane 2 and get our mirror, and what we really want is sketch 2. But it should let us actually capture, the entities. We're not going to be able to do that. There's a couple other things that we can do. I'm going to step out of that, go back to features. There's a couple other things that we can do as well. In assemblies, there's kind of a clever copy entities that you can do, move and copy. But you can't do it to the same degree in a single part sketch, because it doesn't work exactly the same. Bodies to mirror. If I select these 4, I should be able to get it to mirror across this plane. There we go. Okay. It's always a matter of the right settings in SolidWorks because reasons. So we're going to hide these planes in order to be able to just visualize our object. Okay, so we have our version of a unit cell. These are really to do these correctly and finish it off as a unit cell, we would have to look within the boundaries of these planes, and we would have to do a cut using the planes as a reference. I'm not going to go that far because I want you guys just to see the difference of a 111 reference plane and what that looks like. So a first reference plane, let's see if we can do it purely from the section view. So at each of these levels, yeah, it'll let us do a rotation. So we want to do a rotation of 45 degrees. And relative to the front plane, we can see a couple different distances. So at a distance of 0, at an X and Y, both of 45 degrees, we can actually see what this looks like at a distance of 0 at 45 and 45. If we look at it from the front view, we're looking at the cross section, and you can move that up and down through the pattern, but you don't have exactly a complete sphere represented because of the way that this works. So 45-45 gives you, if you look at it from the right side, especially, you have and this is not correct relative to, this is not exactly a 1-1-1 relative to the unit as a whole. So we're looking at it from the right side. If we were doing a 1-1-1, it would be the opposite. So I think it would be a 135. So I think it would be a 135. Let's see. 135. I forget how far that reference angle has to go. So one of our, one of ours is correct. This one, though, in the X direction, X direction is still wrong. So we actually want to go down in the X direction to where it's a 35 there. Yeah, or 45 there. And that gives us and a dimension of 0. So that, let's see, from the front angle, that is almost, we're really close on, yeah. So 135 is a reference there, and a 0 distance. So this gives you at least an idea what that plane might look like. If we bring back in plane 1 and plane 2. So I'm going to leave that section view there for a minute. Plane 1 and plane 2. So everything inside of plane 1 and plane 2, this is what that range would encompass as we look at that section view. So it has if we're looking at the plane, this is our triangular shape that it would form in between them. It's a little hard to show a reference plane. We can get there, but it'd take a very long time to get a reference plane and draw a shape on it. But it gives you an idea, the partial sections of atoms that are represented. So the calculation is not nearly as straightforward on that one. So let's take a look at what that looks like and why. A couple of you are probably never going to want to do SolidWorks again. That's fine. There we go. So going back to this, trying to tie it back to something we understand here. These unit cells, again, you can see on their diagram, the repeat units are the 2D repeat unit here is now like rhomboidal almost. It's now, even instead of triangular, it's almost rhomboidal. So this now has a different mechanism that it needs in order to calculate this. And that's where lots of confusion can come from. So we'll have our height for the unit, which is square root of 3 over 2a, because lots and lots of trig. The area, half the base times the height, gets us back to our repeat unit of 16 root 3 over 3 times r squared, because trust me, I'm a doctor, and we have one complete atom per 2D unit. So that's what we're seeing in SolidWorks. There's parts of multiple atoms that add back up to one whole atom in this repeat unit. And then the planar density is calculated by 1 divided by that. So it's about 7 atoms per square nanometer, or 0.7 times 0.7 times 10 to the 19th atoms per square meter. So the calculation is a little bit challenging because of just that particular geometry, but it'll give you a frame of reference for how some of this works. Okay. Let's get back to this. So they show some examples in the visualizer of atomic packing factors. It's helpful to understand, but we're going to have some XRD labs that we're going to be working from. The X-ray region is here in the spectrum. So it's in the 10 to the minus 6, 10 to the minus 9, 10 to the minus 10 nanometers. And then these will get you where you need to get to in terms of understanding what is happening with the characterization technique. So these wavelengths are going to be bouncing through the material. You can't resolve spacings that are less than fundamentally the actual wavelength that you're using, and the spacing is going to be the distance between the parallel planes of the atoms, and that's the information that you're going to get back. So it looks something like this. You have the incoming rays, and you move you rotate the X-ray through a series of angles so that as you hit, you get an outgoing angle that is proportional to the incoming angle. However, there's some diffraction that happens. So this is why it's called X-ray diffraction. And that change in angle has to do with the wavelength of the material. So you can pick up specific spacings between the atom planes, and especially if there's impurities and things, they're different sizes, etc. There's different interstices are filled, or there's faults. There's all these sorts of things that will get you some information back from. So we'll pick up on this here later this week, but we can based on the angle we can get an idea what the distance is. So as it's sweeping through, it picks up a bunch of reflection through this range, and otherwise the X-rays may be passing through the material. So there's an extra distance here that's traveled by the second wave compared to the first wave, and that difference between the two is how we calculate this distance. So it's a simple geometric process, simple calculation, but it's something that will give us back a chart that looks like this. And this will give us, this is what's called an XRD, or X-ray diffraction pattern. This will tell us something about what do these materials actually look like, since we can't just always draw the crystalline patterns in SolidWorks. It's something that we need to know something about. So we have all of these different spikes for 110. We have a 200 and 211. So this is polycrystalline alpha iron that has BCC crystalline structures, but there are reflections at different X-ray patterns, and that's part of the information that we're trying to understand about it. So the polycrystalline iron means there's these three different crystalline orientations in the grains. This will make a little bit more sense when we pull in some information from future chapters that'll help to clarify some of what's going on here. But we're going to get farther into this. So we'll probably review this briefly for next class before we start working some additional examples. So I know we're about out of time. Questions from today?